So first up we have set theory. And what is a set? Well, a set is a collection of things with something in common, or having something in common, right? So just give that a quick write down. And as I say, you'll want to write down everything here, because this is going to be a nice summary of everything that we did in sets yesterday, right? So if I'm going too fast and you didn't finish write down, just let me know and I'll just go back up, right? Now that we know what a set is, we talked about set notation, right? We saw that you could name a set like a capital letter, right? So we'll call this a set A, and then equals curly brackets. The curly brackets means the set of. And you could write the set of in an English statement. So for example, this says A is the set of numbers from 1 to 4. This is called the set builder form. Okay? Or you could actually just write out the elements. So A is the set of 1, 2, 3, 4. This is called the roster form. Now of course, if a set has many elements, or even infinite elements, then writing the roster form might not be practical. There is a third form that we have to learn, and we are going to learn that today. Yeah. So when we're talking about sets, we have some types of sets here, and one of them is a finite set. A finite set has an end. It's an end. It has an end. It's a small set. So for example, the set A being 1, 2, 3, 4, that's it in the whole set A. Just 1, 2, 3, 4. So this is a finite set. An infinite set has no end. So we could take this example, the set B being the set of ... So we could see there that it coming from this direction, right? And it coming from the negative numbers, -2, -1, 0, 1, 2, and then it continuing into the positive numbers there. And it goes on to infinity, right? So an infinite set has no end. Then we spoke about the universal set. Remember, this is just a quick review of everything, but you are going to want to have to write it down because it's a nice summary, and you'll have everything in your book in a list, right? So the universal set is essentially the set of everything. Everything that is relevant to our question. And please remember that in a Venn diagram, the universal set is often shown as a triangle, right? Not a triangle, sorry, a rectangle. Sorry, I've been at it all day. Yeah? So a rectangle is what we usually use for the universal set. I hope you guys are writing it down, right? Next, we start to talk a little bit more about set notation and how we write sets. We spoke about it already, how the name of a set is usually in a capital letter. The elements of the set are usually written in common letters. And you know that these things that the set has in it, the things, a set is a collection of things. So these things are elements or members, right? And this is how we write the element. So we could see here that the element, the member F is an element of the set A. Notice the element is written in common letters and the set itself is written in capital letters, right? We can see here that Z is not an element of set A, because set A only goes from A to F. So Z is not in this set, right? So that's how we write these kind of things. When it comes to equality, two sets are equal if they have exactly the same members. Exactly the same members. So we could see here A is 1, 2, 3, and the set B is 3, 2, 1. Well, guess what? The order of the elements does not matter. So yes, they are both equal. They do both have exactly the same numbers. So A is equal to B. And we were here talking about the equality and the sets being equal. The order of the elements does not matter. So these two sets, A is equal to B, they are both equal. Now we have to talk about subsets. Now a subset is a smaller set that is completely inside the bigger set. Completely. The entire thing needs to be inside, you know. So we could see here that, and in terms of a Venn diagram, if I have this set A, this set A is 1, 2, 3, 4, and we could see the set B is 1, 2. So notice how B is totally inside of the set A. So we could say that B is a subset of A, and this is how we write that. Now this particular symbol stands for a proper subset. And I want you to remember the word proper. The word proper, you could think about it as the word normal. Right? This is what a normal subset would be. When you have this subset being smaller than the larger set. And so the entire subset fits inside of the larger set. That is what we think a subset should be. So that is a proper subset. And notice the symbol for a proper subset is as a sideways horseshoe. We could see here the set C is the set 5 and 6 with 5 and 6 in it, the set C. That is not in the set A. That's a different set altogether. So therefore C is not a subset of the set A. So everybody cool so far? Anybody have any questions? Do you all think I'm going too fast? Alright. Okay, nice, right? Because I know you all, I would really like you guys to write this down. Now, a proper subset, as we could see, is smaller than the larger set. So that is how we expect a subset to be. We expect a subset to be smaller and inside of a larger set, like one of those Russian dolls, right? But an improper subset now. A set is improper. It's improper. It's not normal, right? When its elements are equal to the parent set. So we can see here the set A is 1, 2, 3, 4. The set B is also 1, 2, 3, 4. But guess what? I could say that all of set B is inside of set A. I could very well say that, and that wouldn't be wrong. That's true. All of set B is inside of set A. However, if you really check it, set B is equal to set A. They both have the same amount of elements. So we call that an improper subset. And you notice the sign for an improper subset. You notice how an improper subset have this kind of equal sign in it. Yeah? So that is how it is know an improper subset. You just see the little equal piece here, right, underneath the subset sign. So B is an improper subset of A, which means that B has the same amount of elements as A, right? Then we talked about the empty set or the null set. So the empty set is a subset of all sets. The empty set is a subset of all sets. And the empty set, because the empty set is also an improper subset of itself. See if that one makes any sense to you, right? Remember, the empty set is empty, so it has no elements. So we could call the empty set by this symbol here, or we could just use curly brackets that have nothing in it. Yeah? So let me know if I'm going too fast. Order or cardinality. And this is one of those things that all of the students they seem to forget by the time they reach Csec level and they ask earlier where's the cardinality of a set. Everybody just seems to forget this, but it's actually really easy. The order or cardinality of a set is given by the number of elements in the set. That is all that it is. So we can see here that the set A is A, B, C, D, E, F, 1, 2, 3, 4, 5, 6. You have 6 elements, so therefore the order of A is 6. Last week or last class, we were actually talking about how can we find what are the total amount of subsets in a given set. And we did an experiment. We had a set with 1 element and we counted the subsets and saw that we have 2 subsets in that set. Then we had a set with 2 elements and we saw that there were 4 subsets. And a set with 3 elements, we saw that there were 8 subsets. A set with 4 elements, we saw that there were 16 subsets. And a set with 5 elements, we saw that there were 32 subsets. So, is there a way for us to create some formula where we can figure out what is the total amount of subsets in any set? Right? And did anybody figure it out? Caitlin, Ariel, anybody figured out this? No idea? Alright, cool. Well, if you want to find out, if somebody give you a big set and they ask you to find how much subsets in there, obviously you're not going to list out all of the elements because as you could see, 5 elements is 32 subsets. So if you have 10 elements, then imagine the amount of subsets you're going to have. So there is an easy way, and I told you what to do is to break this down by 2's, right? So let's try. For this one, we just have 1, 2, right? For this one, we have 2 times 2, so that's 2 2. For this one, 2 times 2 times 2. 2 2s are 4 2s are 8. For this one, 2 times 2 times 2 times 2. 2 2s are 4 2s are 8 2s are 16. 2 times 2 times 2 times 2 times 2. 2 2s are 4 2s are 8 2s are 16 2s are 32. So obviously we can see that there is a pattern there, right? The pattern is, if you look at it, the amount of elements that you have is the amount of 2's that you have. Yeah? So if I have 2 elements, I have 2 2's. If I have 3 elements, I have 3 2's. If I have 4 elements, I have 4 2's. So therefore, we could say that this here is 2 to the power of 1 because I have 1 element. This here is 2 to the power of 2 and I have 2 elements. This here is 2 to the power of 3 and I have 3 elements. For 4 elements, I get 2 to the power of 4, and for 5 elements, I get 2 to the power of 5. Right? So therefore, the total number of subsets for a set with n elements is simply 2 to the power of n. Yeah? So 2 to the power of n, where n is the elements in the set. Right? So if I had a set with 8 elements in it, how many subsets would there be? 256, which is 2 to the power of 8. Yeah? Example, the set A has an order of 8. Right? Therefore, the number of subsets is 2 to the power of 8, which is 256, you said? Nice. So everybody write this down. Can I move on? moving on. Right. So now we get into some slightly new material, but everybody should still kind of remember this, right? The union, right? Now we're going to talk about the union. A union includes all of the elements from many sets. Many sets. All of the elements from all of the sets is what I should have said, right? So we can see here the example. We have the set A, which is 1, 2, 3. We have the set B, which is 3, 4, 5. And we have the set C, which is 5, 6, 7. What I want is I want A union B union C. So that means that I want all the elements from all the sets. I want all the elements from A, from B, and from C. So what do I get? 1, 2, 3, 4, 5, 6, 7. Now wait and notice something. Set A has the 3 in it. Set B has 3 in it. But yet I only wrote 3 one time. Right? So remember, right, that you do not repeat elements. Do not repeat elements. Because some people will want to go and write 1, 2, 3, 3, 4, 5, 5, 6, 7. But no, you don't repeat your elements, right? Next up, we have intersections. Now, this will only include the elements that are common to both sets. Those elements that are common to both sets. For example, I have the set 1, 2, 3. I have the set 3, 4, 5. I have the set 5, 6, 7. Right? So A intersect, and notice the sign for intersect is the upside down horseshoe, is like an N for intersect, right? And for union, it was like a U for union, but it's not a U, it's like a horseshoe, right? Yeah. So the N is for intersect, the N horseshoe is for intersect. So we can see here that A intersect B means that I only want those elements that are common to both A and B. So if we see here that 3 is common to both A and B, so A intersect B is just the set with 3, right? B intersect C, we can see here that B has 5, C has 5. So B intersect C is the set with just 5 in it. And A intersect C, if we look at it, A is 1, 2, 3, C is 5, 6, 7. So there is no intersection. So A intersect C is the empty set. It is empty. There is no intersection there. Everybody finish write this? Can I move on? Now you see now why I'm telling you to write everything down. Because once you write everything down, then you would pretty much have the entire topic of sets on one page. So whenever you're revising, you can just look at that one page and literally we are covering the entire topic here, right? The complement means everything that is not in the set, right? Everything that is not in the set. So for example, if I have the set A, B, C, D, E, F, and then I have the set B, which is C, D, yeah? What I want is I want B complement. B complement is everything that is not in B. So that means that this C and this D, I don't want that. I don't want anything that's in B. I want everything else. So this C and this D gone, I'm being left with A, B, E, and F. So A, B, E, and F is B complement, right? the difference of two sets. Now this is something that a lot of students often make mistakes and mix up, right? All elements from one set must be removed. Notice that word all is in capital, it is underlined, and I draw two boxes around it. So that must be a really important word, right? All elements from one set must be removed. For example, I have the set A. The set A is 1, 2, 3, 4. I have the set B. The set B is 3, 4, 5, 6. You could tell that A and B intersect. 3, 4. Right? So look, I draw this little Venn diagram here to show the relationship. This is the set A, 1, 2, 3, 4. This is the set B, 3, 4, 5, 6. And this shows the intersection here of A and B. You could see them intersecting. However, I want to find the difference, A minus B. So you see this B that's being minused here? That means that I want to remove all of the elements that have anything to do with set B. What I like to say is when our friends set you up and you say, you know what, over's that friend, yes? And you have nothing to do with the friend, you know? So you delete the number, you throw away all the gifts that they ever give you. Everything that had to do with that friend, you let go of. So if you look at it, A minus B means that I am letting go of every single thing that has to do with B. So I don't want nothing. Now at the end of the day, remember this 3 and this 4, that is part of the set A. But it's also part of set B. And I don't want nothing to do with set B. We vex with set B. So set B getting thrown away. Anything to do with set B getting thrown away. So what are we left with? We're just left with whatever little set A has in it. So look at it. When you write A minus B, it is the second one, the B, that you are getting rid of. Does everybody understand the difference of sets?
That if you're writing A, like the total of A minus the total of
You mean the actual numbers?
A. Like 1 plus 2, so that's A.
Right.
5 plus 6.
Right.
Then 4 is that 3 and 4. So it come like it just minus them 1, 2, 3, the total of 1, 2, 3, 4.
No. It's not. First of all, the difference here has nothing to do with numbers. Remember, a set doesn't necessarily have to have numbers in it, right? Yeah. So a set could have, you know, and if you want, we could do like a quick thing. Let's just say the set U. Oh, not U. Alright, let me just say the set W is things that we wear. Alright? Things you wear. So that would be what? What's things that you wear? You could have like a cap or a necklace or shoes. Right? Dot dot dot. And let's call the set F what could we call the set F? Things on your fingers. Right? So you have rings, you have Yeah, you have polish. You do have nails. You have hair on your fingers, right? For some of the guys here, right? And that kind of thing. And if we look at it here, the Venn diagram for this, you know, we have the W and the things on your fingers, F. So obviously, hair is not something that we wear, it's just something that we have. Nails is not something that we wear, it's just something that we have. But we wear rings, we wear polish, so that will actually go into the wear part of it. And then we also wear caps and shoes and etc. Right? Now if I was to have W minus F, that means that everything in F, whether it intersects or not, everything in F I am throwing away. Yeah? So if I throw away that, that means that W minus F is just going to be caps and shoes. Now, this is super important, right? And take your time and write this one down, because this is something that you're not only going to see in set theory or in set questions. This is something that you will have to face in every single topic in mathematics. Yeah? And these are, because you know maths is a couple of things, right? What did I say maths is? We have things, which are numbers, and then we have what we do with those things, what to do with those things, and those are operations. So we can add those things, minus those things, multiply and divide those things. Yeah. So the thing is that we're looking at the things, the numbers, and we realize numbers, they have different types of numbers. We have different sets of numbers. So you have to, as a mathematician or a math student on any level, you have to know all of these types of numbers here, right? Actually, for Csec level, you don't really have to know this one. So you don't have to write this one down, right? You don't have to know imaginary numbers either, but they are fun, yeah? But you don't really have to know imaginary numbers either. Okay? But you do have to know all of these. Alright? Now, the first one are your natural numbers. And those natural numbers are known as counting numbers. So we count 1, 2, 3, blah, 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 blah. Right? It's an infinite set. All of these are infinite sets, of course. Right? So natural numbers are the numbers we use to count with. Okay? Whole numbers, well, look at that. Whole numbers have all of the natural numbers in it. But whole numbers include 0. You notice natural numbers do not include 0. Yeah? Natural numbers don't include 0. So don't make that mistake. If somebody talking about 0, they're talking about a whole number. 0 is not a natural number. Natural numbers are only positive, as you can see, and whole numbers start with 0 and go up the positive natural numbers. So let me ask you something, right? I have two sets here. One set is natural numbers, the other set is whole numbers. Which one of these are the bigger set, or is the bigger set? I have whole numbers as one of my answers. Anybody else? Which one of these is the bigger set? Why? Why whole numbers? Right. So whole numbers, look at this. you have all of the natural numbers inside of here, and then it have one extra. So yes, whole numbers are bigger by one, and that is by one element, and that element is 0. Can I say that the natural numbers are a subset of whole numbers? Can I say that? Alright, yes I can. Because you could see here that all my natural numbers can be found inside of the bigger set of whole numbers. And if you look at this here, right? We have integers next, and notice natural numbers is n, whole numbers is w, integers we use z. We don't use I, we use I for irrational. So integers we use z. And if you look at the integers, you have all of the natural numbers in here. You have the 0, which means you have all of the whole numbers in here. But now integers, we include the negative numbers. Yeah? So integers is where we include negative numbers. Can I say that whole numbers are a subset of integers? Yes, because if you look at it, the entire whole number set is inside of that integers set, right? So we have natural numbers, and pay attention to the question that I ask in all of the subsets questions. Natural numbers are a subset of whole numbers. Whole numbers are a subset of integers, right? Now let's talk about rational numbers. And rational numbers, we have the Q. Q, you have to know all of these symbols by heart. A rational number is when you have two integers and you put one over the next one like this. So where's that? That's a fraction. So I have two integers like that, and that gives me a fraction. So this is a rational number. I have two integers, one over the other, and it gives me a fraction, an exact fraction. So this is what a rational number is. Right? Rational numbers are fractions. Right? So would you say that integers are a subset of rational numbers? So Shizzy?
No.
No. Okay, I have a no from Shizzy. Anybody else? Can I have, in order for integers to be a subset of rational, that means that inside of here I need to have integers. I need to have integers inside of here. So do I have any integers? Can integers be expressed as a fraction?
Yes.
How? Where's the number 2 as a fraction? 2 over 1. Where's the number minus 3 as a fraction? Minus 3 over 1. So yes, the integers are a subset of rational numbers. They can be expressed as a rational number. Right? So you have all of your integers. All of your integers are inside of the rational number set. So you have these whole numbers, all of them over 1. But then you also have other numbers that are not integers, like 3 over 4, for example, or 23 over 25. You know, these are not integers. So these are in your rational numbers set as well. So you can see as we go down, the sets keep getting bigger and bigger, right? Now after rational numbers, we now have irrational numbers, right? An irrational number is a number where we do not know the true value. It is a number that cannot be expressed as a fraction. So rational numbers, for example, a half is 0.5, and so this is a rational number. Decimals are inside of the rational numbers because a decimal is a fraction. It's an exact fraction. But if we look at it, irrational numbers are not exact at all. These include numbers that do not have an exact value. For example, the square root of 2. If you punch the square root of 2 in your calculator, you will get a non-terminating decimal. Somebody punching the square root of 2 and tell me what it is?
1.4142135562. ...
If it is that your calculator had more spaces, you would have gotten more numbers. In fact, this decimal goes to infinity. There is no human being on the planet who could ever know the real exact value for the square root of 2.
Why is that like that?
Huh?
Why is that like that?
What do you mean, why is that like that?
Like, why can't we know the exact value?
Well, I mean, we tried, right? We tried to work it out, and the answer for that question, we'll have to get into all kind of Pythagoras Theorem and thing, right? And if you remember Pythagoras Theorem, and we'll do Pythagoras, you have a triangle. This side is 1, this side is 1. So the root is 1 squared plus 1 squared, the hypotenuse, which is, and that is c squared. So therefore c squared is equal to 2. C is equal to the square root of 2. So at the end of the day, and this is a beautiful, wonderful thing about mathematics, right? You have a triangle here that have this side is 1, you could easily draw that. This side is 1, you could easily draw that. And therefore, by Pythagoras Theorem, this side is supposed to be the square root of 2. So yeah, you could see the square root of 2 right here in front of your face. You could see it. But we could never know the exact value because the decimal goes on to infinity. It just keeps going and going and going. And there are many numbers like that. Many numbers. In fact, there are so many numbers that we have an entire set describing them, irrational numbers. Yeah? The square root of 2, the square root of 3, the square root of 5, they're all irrational. You know what's another irrational number? Pi. Pi is an irrational number. Pi is 3.1416 blah 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 going down the road to infinity. Nobody could ever know the true exact value of pi. In some questions, we use pi to be 22/7. Yes, this is a rational number. Yes, this is an exact number. But this is not the real pi. This is an approximation. This is a fraction that will give us the closest possible value for pi. But it's still not the real thing. Yeah, we could never know what the real value of pi is. Right? And if you want to, Scotia, you could very well go ahead and try to find out what number that when you multiply it by itself will give you 2. X squared is 2. Therefore, x is the root of 2. So what number, when you multiply it by itself, gives you 2? you'll see that it's harder to find than you think. Yeah. So everybody understands what irrational numbers are? Any questions? All right. Let me ask you something. You can see that this is a subset of this. This is a subset of this. These are a subset of this. This is a subset of. Is this true? Is this a subset? Are rational numbers? Can rational numbers be found inside the set of irrational numbers?
I would say
Anybody else?
no.
No, very good. Because these are numbers, irrational numbers are numbers that do not make sense. So you can't have numbers that make sense and put them in a set of numbers that don't make sense, because that don't make sense. So irrational numbers is a set all by itself. And then we have this guy, real numbers, and that includes all of the above. So in terms of sets, what would real numbers be? What kind of set would real numbers fall into? Yes. Real numbers would be your universal set. Real numbers would be your universal set. So here's what. I am going to give everybody, let me see, yeah? Oh yeah, alright. Alright. So did everybody write this down? Everybody understand, right? Okay, next. There's just 2 more topics we had to do again, and then we'll get to some questions, right? So remember we had the roster form and we had the set builder form. Well, this is another different form, and this is called the algebraic form, right? Algebraic form is another way of writing sets using algebra, right? And this is why I did algebra before I did anything else, because algebra does play a role in everything. So what do I have? I have a special way of writing this out. And if you was to write this in set builder form, it would have to be, it would be a long paragraph. So this is why algebraic notation is really, really simple, right? But you have to be real careful with it. So let me show you what it means. The set A is the set of. Remember that curly brackets means the set of. The equal sign could stand for is. So the set A is the set of numbers. Right? That X stands for numbers. They could be any numbers. Remember, X could be anything. So the set of A is the set of numbers such that. This means such that. Yeah? Such that the numbers are less than 5 but they're greater than 1. The numbers are less than 5 but they are greater than 1. So that means when you see this X here, you could see that X is lying somewhere between 5 and 1. It's larger than 1, but it's smaller than 5. Where X is an element of whole numbers. So they're telling you, yo, X is an element of whole numbers or maybe even natural numbers, but it is not rational or irrational. So you do not have to include 2.5 and all of that kind of thing. Just keep it to whole number. Now notice something. This less than sign does not have an equal with it. This is where it gets tricky. This less than or greater than sign does not have an equal there. So that means that this set does not include 5 and it does not include 1. It just includes the numbers between 1 and 5, but it does not include the 1 and 5. So that means that this set will actually be the set 2, 3, 4. If we look at set B, same thing. The set B is the set of numbers such that those numbers lie between 1 and 5. But look, we have less than or equal to. Yeah? So because we have the less than or equal to means that the 1 and the 5 is included, where x, the number, is an element of whole number. So it's a whole number we're dealing with. So now we could see that the 1 and 5 is included. So this set is 1, 2, 3, 4, 5. And if you look at this set here now, and that's why you need to be careful, the set C is the set of numbers such that those numbers are between 1 but not including 1, and 5 but it includes 5. Right? It does include 5. You could see here it's equal to 5, but it's not equal to 1. It's greater than 1. Right? So you could see here that x is between 1 and 5, including 5, where x is an element of whole numbers. So it doesn't include the 1, but it does have 2, 3, 4, and it does include 5. So, Soraya, do you understand this algebraic notation thing? Right. Well, I hope that that it does make sense for you. And there's, as I say, there's a way to read it. Right? The set A is the set of numbers such that the numbers are between 1 and 5, where those numbers are whole numbers. Yeah. Imagine if you had to write this out in set builder form. If you had to write this out in set builder form, then that's a whole paragraph you had to write out there. So the algebraic form helps us. It helps us to write a little easier. Soraya, do you understand this this less than and equal to range business? You understand that, right? Alright, so you understand how it doesn't include 1 and 5 here, right? And you understand why it does include 1 and 5 here, right?
Yeah, but the notation is
Alright, yeah, but it's not difficult. I mean, you, if it's one thing you should have learned from me, Soraya, is that algebra is not hard at all. Algebra is actually quite easy.
I do just need to have it's not taken all day, but it's all.
Yeah, I think you you have this fear of algebra, and that fear is what keeping you back. But really, algebra is quite straightforward, right? So you need to try to let go of that fear, right? And now we're talking about Venn diagrams. So I want.
Are you the mathematical form of Yoda?
I am Yoda, actually. Actually, I'm not Yoda. I'm more of a right now at this stage in my life. I'm more of a Anakin Skywalker episode 3.
Why did I do that?
Yeah, like I'm that close away from killing everybody, you know. Anyways, these here we're talking about Venn diagrams, and everybody have some clue as to what a Venn diagram is. So take 2 minutes and see if you could do the Venn diagram for this. Alright, alright, a way to do 2 Venn diagrams for me, right? Just now. Right, so this here is question 1, and this here is question 2. So we have 2 Venn diagrams. Right? I want you to draw a Venn diagram to represent these sets here. You can see that we have a universal set that is represented by an algebraic form, and then we have some maybe subsets or not, I don't know, that they are listed out here. So I'd like you to draw the Venn diagrams for this, As well as, and this one is absolutely a challenge here, I want you to draw the Venn diagram that represents all of the numbers in terms of sets. So let's get with this first one now. In terms of Venn diagrams, this first one should be easy. Now we see here the universal set. The universal set is always called U. So once you see a set called U, you can assume that's the universal set. So the universal set now is what? U is the set of numbers such that those numbers are between 1 and 10, including 1 and 10, where those numbers are natural numbers. So you don't have to deal with a half and a third and all that kind of thing. You have natural numbers here, so you're just dealing with normal numbers. So I'll put, remember, my universal set is always a rectangle. So you will lose marks if you did not have a rectangle for the universal set. So that is U, right? U is the set of numbers such that those numbers are between 1 and 10. Nice. Now let's check the rest of the sets here. We could see the set A has 1, 2, 3, 4. We can see the set B has 3, 4, 5, 6. And the set C is 3, 4, 7, 8. So let me ask you something. Because we have to draw these sets in here now as circles. But we should know, do they intersect or not? They do. Which ones intersect? All three of them intersect. So I'll definitely want to put three circles where all three of them are intersected. So that's set A, that's set B, and then I have set C over here. Right? So what is inside of this intersection here? We can see here that all three of them have the numbers 3, 4, 3, 4, 3, 4. So that 3, 4 is going to be inside of the intersection of all of them. So that 3, 4 is in the set A. It is also in the set B. And it is also in the set C. So we can see here that we have 1, 2 being a part of the set A. We have 5, 6 being a part of the set B. We see here that there is no intersection here between A and B alone. We see here that there is no intersection or nothing in this set between B and C alone. Similarly, nothing in this set between A and C alone. Right? So what do we have here? In C, we have 7 and 8. Very, very nice. So is this what you guys got? Right. Yeah, very good. Very good. So I was testing to see. Remember, the universal set are your numbers between 1 and 10. So therefore 9 and 10 are going to be outside in the universal set. 9 and 10 are not in A, they're not in B, they're not in C, but they are in the universal set. Right? Soraya, are you okay with this?
Yeah,
Beautiful, lovely, very nice. What about this one? That is fine, no scene. What about this one now? What do you guys got for this one? What is the universal set first of all?
Real numbers, so it consists of all.
Right, so first of all, the universal set U is, and I'll write it in algebraic form, the set of numbers such that those numbers are real numbers. You see how I write it in algebraic form? All the real numbers, right? So what now? Let's start with the smallest set. The smallest set is the natural numbers, right? So I have the natural numbers here. And the natural numbers, all of the natural numbers are inside the set of whole numbers. So I'll have the set of whole numbers here. And all of the natural numbers are in there except for 0. 0 is the only thing that is outside of natural, right? So these are all of my whole numbers. And now let me just write that up inside so that you know the whole numbers, right? And then all of my whole numbers are inside the integers. So I'll have another set here. And these guys are my integers. And in the integers, you can see that I have the full set of whole numbers. I have the full set of natural numbers. But the ones that are going to be outside here are my negative numbers. -1, -2, -3, ... So my negative numbers outside here, but the positive numbers are inside in the subsets over here, right? But then all of my integers can be found inside of the rational numbers. So now I have a next set like this. Where all of the natural, the whole, and the integers can all be found inside of rational numbers being Q, right? Q is for rational numbers. And what's going to be on the outside? Well, your normal fractions like a half, -3 on 4, you know, and that kind of thing will be outside here. So your fractions are going to be on the outside, and on the inside you'll have the whole number fractions like 2/1 or -3/1, you know. And then now, I have irrational numbers. Now we can see that irrational numbers are kind of a special thing by itself. The rational numbers are not in the set of irrational numbers. So we could put that set of irrational numbers outside here. And these are my irrational numbers, like the root of 2 or pi or anything like that. Phi even is an irrational number, right? So we can see here that the irrational numbers, they are in the universal set of real numbers, but they are not included in the rest of these sets here. And this here would be the Venn diagram showing you how all of the numbers in maths are basically in sets, in groups. We just grouped all of the numbers in the universum. Yeah, remember the only ones we deal with here, we didn't deal with the imaginary numbers because those are imaginary, they don't exist. And the complex numbers also have an imaginary part of it. So complex numbers technically don't exist either. So we basically just draw a Venn diagram outlining all of the numbers that exist in math, right? Soraya, how you feel about this one? Alright, so check this one out. You all seeing this, right? So which of the following are sets and which are not sets? A, is A a set?
Yes. Yeah.
Yes. Alright, is B a set? Why not? Right. So remember, a set is a collection of things that all have something in common. Now, the collection of all difficult questions in a chapter on sets. Difficult is subjective. I might find something difficult, Soraya might find it easy. So therefore, this is not a set because there is no definition for what a difficult question is. Yeah? The collection of girls in your classroom, is that a set? Collection of rivers in India.
Yeah.
Collection of all active teachers in the school.
No.
No, it is not. We don't know what an active teacher is. Right? Collection of all integers more than -3.
Yeah.
Collection of all beautiful flowers in a park.
No.
No, because what I might find is beautiful, Shazay might find is ugly, right? So, I don't know. Right. So we have these sets here. State whether it's true or false. Is number 2 true or false?
True.
Alright. Soraya, is this here true or false? True or false? This one here. Huh? False, yes. It is false, yeah. They're saying 36 is not an element of D, but we could see here that 36 is an element of D, so that means they are lying. Right? So write the following sets in roster form. Right? So you actually have to write out the elements. And you can see here that they start by giving you the set builder form. So I'll just do a couple to show you. First of all, let's just see. Number C. The set of integers lying between -2 and 2. So that means that the roster form C is the set of integers lying between. They never said including the -1 integers. So 0 is an integer and then 1 is the other one. And they never said 2. Yeah? So that is, so you have to actually write out the elements there, right? Now they give you algebraic form as well, so you have to be able to read it, right? So G is the set of numbers such that those numbers are elements of natural numbers, and those numbers are between 5 and 12, but they do not include 5 and 12. So obviously G would be 6, 7, 8, 9, 10, and 11. That is the set G. So everybody understand what to do for this page, right? I hope so. Right? And then they give you here a list of sets in roster form where they actually list out the elements, and you have to write it in set builder form. Yeah. So first of all, well, I ain't gonna give away too much, right? But you have to actually write the set builder form for it. They give you a bunch of sets here, and you have to give what the cardinal number, the cardinality, or the order of the set. For example, the set of months in the year. So the order of X. The order of X is 12. Because we have 12 months in the year, right? Unless you're dealing with the pagan calendar, of course. So yes. Then here what we have, they give you set A, B, and C. Which of the following are considered as universal set for all of the 3 sets? So they give you 3 sets, and they want to know which one of these could be the universal set for all of these here. Right? Then find the number of proper subsets of the following. So this is where you'll have to use your 2 to the n to find the number of subsets. B, I don't know how they're gonna do B, but B looking quite evil. Yeah, B is an evil one. Actually, no, not really. Okay. Nice. Number 8. This is where we're dealing with unions and intersections. Over here, they give you 4 sets, and they ask you to find all of these unions and intersections here. These questions here, they give you four sets, and they ask you to find these differences. They ask you to find complements and unions with intersections and all of that stuff. Same thing over here. Complements. Find the complement of the following. They don't want you to find what A complement is, what B complement is, what C complement is, and they're giving you what B is, so you have to find what B complement is, right? That's what it is. Pretty okay. And number 14, we just have this is some cool stuff. This is some cool stuff. This is where set theory will start to get really interesting, right? This is when it'll start to blow your mind. They give you these 3 sets here, and they asking you you have to prove that P union Q is the same as Q union P. Yeah? You have to prove that P union Q all union with R is the same as Q union R all union with P. So you had to prove them things, and this is really where sets to start to tax your brain, right? Same thing with this, right? These here are actually 2 important theorems that you guys need to memorize and know, right? And they could be really helpful in sets questions. And I think this here is just more sets questions on some other worksheet somewhere. All right, that's it, guys.